The problem is pow. You create a power function, obviously without using the built-in power function. So for example, 2 to the 10 is 1024. So, I mean, what is a power, right? A power is, and my tablet's not working. There we go. Right, so what is a power? A power is a number multiplied by itself over and over, right? So like 2 to the 10 is 2 times itself 10 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we wanted to do this brute force, or not even, it doesn't even sound like brute force, but linear time, we would just, we literally just say, so we have x equals 2, n equals 10. So we just say while, as long as n is greater than 0, we just take x multiplied by itself, right? So we'd take, maybe take some result, set that to x as a starting value, or it might even be 1, I think. I would say while n is greater than 0, we would just say result times equals, which, okay, maybe I should asterisk, times equal x, right? And then we just decrement n, and then return a result. And that, kind of works, but actually for the test cases they have, it won't work, just because they have n that goes up to, n can go up to 2 to the 31 minus 1, so like, what is that, like 2 billion or something? So that won't work. But what we can recognize here is that there's a lot of repeated work, right? You're repeating this process of 2 times 2 over and over. And that's the whole idea of exponentiation. So if there's some way to recursively do this, like dynamic programming, right? Divide and conquer, however you want to think of it, pretty much like save ourselves from doing work over and over. So if you did, for example, so this is when n equals 10, right? Let's say we just take half of that and say, okay, so n equals 5. What's the answer for that? Well, let's keep this dividing process going. Let's divide it by 2. Let's just floor it in this case. So we'd say, okay, let's just do this. Okay, so n equals 2. What's this? Okay, I don't know. Let's keep dividing. Okay, here, n equals 1. Now, when n equals 1, this is a base case, right? When n equals 1, we'll just return x. So we'll return this back up here. And our result from the, the previous recursive call will be 2. And here's what we'll do. We'll say, at this point, of course, anytime n was 1 in the previous call, it's going to be 2 here. So we could just multiply this by itself, right? So we'd say 2 times 2. And just to be clear, we're not multiplying x by itself. We're multiplying the result from the previous recursive call by itself. You'll see that in these later steps. So we'll multiply by 2, and that equals 4. And then we'll return this up here. So now we have 4. So we'd return 4 times 4 here, right? Which would be 16. So notice how we're multiplying 4 times itself, not 2, right? X is 2, but we're not actually multiplying x by itself. We're multiplying the recursive result. But the problem here is this would equal 16, yet we know 2 to the 5th is 32, which means we really need to multiply this by x again. So the way to write this in the code is to pretty much say if n is odd, we'll tack on another x, right? So this would be 32. And now up here, n is 10, that's even, so we don't need to tack on another x, so we just do the result, 32 times the result, which equals 1024. And so our base case is n equals 1. I'm not sure if it's actually needed, but you can slap in a base case of n equals 0. I suppose it wouldn't ever be that, but I had it in the code anyways. And we'll have to deal with another base case later, but let's write that for now. So base case 1, if n equals 0. And again, I don't know, I'm thinking this isn't actually needed, but it doesn't hurt to leave it in there. Actually, we're not going to put it in there. We'll see if the code works without that. So the base case, we talked about n equals 1. If n equals 1, we'll just return x, right? Now this is the recursive case. So we want to get the recursive result. So it would be the function with x, because x doesn't change, but n does change. We divide n by 2 each time in order to divide the problem down. So we take this and we say, okay, the result we want to return here is going to be the recursive result times itself. And that works for the cases where n is even, right? Like here and here. But if it's not even, we want to add another, or not add rather, but tack on, multiply again, another x. So we'd want to say result, we'd say if n is odd, we'd want to multiply the result by x again, just to get that odd x that we need. And then we return result. Now this won't work for all the test cases, but it should work for some of them. And the reason why is because we're not taking care of the cases where n is negative. Let's just make sure that's the case we fail on. Should be. Okay, exactly. Negative. So when n is negative, let's just take the example they gave us, which was 2 times 2 to the negative 2. So n equals negative 2, x equals 2. So this answer should be 1 over 4. How do we get that? Well, the way negative exponents work is you take the number 2, you put it over 1, and then you multiply it by the absolute value, or you raise it to the power of the absolute value of this. So 2, which of course is 1 over 4. Another way to think about it is to just drop the negative, get the answer, which is 4, and then inverse it or reverse it or whatever the term is. Put it over 1. Rather put 1 over it. So the way to do this in the code, I mean, we're doing the same process, right? If you just forget about this, we're doing the same process. Like for example, 2 to the negative 5th would be 1 over 32, right? We're taking, like I said, dropping the negative, finding the answer, right? 32, and then just tacking on a 1 at the end. A 1 over at the end. So the way to do that in the code is just another base case. We just want to check. Because really what's going to happen is, let's say x is 2, n is negative 5, right? So we're going to do the same process. We're going to say, okay, keep x the same. We're going to divide this by 2, which would be negative 2, right? So n equals negative 2 down here. Still having a base case, so now it's still 2, and divide this by divide this by 2. Negative 1, so n is negative 1. Now this is kind of a base case. It's not actually a big base case in our code currently, right? Because we have only 1, but it is a base case, right? If we get to this point, we know we're done. We know anytime we divide this by 2, I don't know, it'll stay negative. I don't really know what's going with that, but because technically that'd be 0. Wait. Okay, well that's just Python for you. Because if you did that, it'd be 0. But with negatives, it stays as negative 1. So that's a problem, right? So we know that's a base case. This would just be an infinite loop. So we need to kind of recognize this as a base case. So if n equals negative 1, what do we want to do? What do we want to do in this case? What do we want to return? Well, normally, if it wasn't negative, it was just 1, we just return this value, right? But the whole idea of the negative is we inverse it. Right? We put a 1 over x, or rather x to the n, whatever it is. So why don't we just do that here, right? Because 1 times itself is just 1, right? So if you have a fraction like 1 over 2, and you put it multiplied by itself, that's 1 over 4. And you take 1 over 4 times itself, that's 1 over 16. And you keep that process. Notice how the 1 doesn't change. So why don't we just slap the 1 on right here? So that's what we'll do. Just another base case. Do that, right? Or not. See, okay, so yeah, the 0, we did need the 0 base case just for the only time it would actually be needed is when the actual n is 0. Obviously, if n starts as any number that's not 0, we're never going to get to 0 by dividing by 2. But in the case where n actually is 0, we need the base case. And of course, any number to the power of 0 is 1. So we return 1. There we go.